Liquid-tight flexible metallic conduit, or LFMC, as defined by the National Electrical Code, Section 350.30 FR, permits its underground use under specific conditions. Firstly, it must be enclosed in raceways, sleeves, or cables approved for underground use. Secondly, it needs to be protected from physical damage. Thirdly, the conduit must not be subjected to excessive moisture. The suitability of LFMC in a given situation depends on how it adheres to these protective measures. In this context, the rigid metallic conduit extending from the meter socket to the back porch slab offers a degree of protection against physical damage and moisture. However, the segment of liquid-tight flex transitioning from above the slab to beneath the residence might face vulnerability to physical damage due to its exposed positioning. Consequently, two options are presented. Option 1, which is highly recommended, involves using rigid metallic conduit for the entirety of the feeder run, extending from the meter socket directly to the original panel. This approach guarantees comprehensive safeguarding against both physical harm and moisture infiltration. Option 2, while potentially viable, necessitates heightened caution. If LFMC is chosen, ensure its complete enclosure within a PVC conduit or another approved raceway suitable for underground applications. Additionally, meticulous sealing at all entry and exit points is crucial to impede moisture ingress. Moreover, the conduit must be fortified against physical damage, potentially through encasement within a concrete slab or alternative protective methods. Additional considerations include consulting with local building inspectors or qualified electricians to ascertain specific requirements and secure necessary approvals. Adherence to all manufacturer's instructions pertaining to the installation of LFMC and all other electrical components employed is paramount. Verification that the entire installation complies with the applicable stipulations outlined in Chapter 3 of the National Electrical Code, which pertains to wiring methods, is mandatory. It's imperative to emphasize that the NEC provides a comprehensive framework for electrical installations, ensuring safety and compliance. When dealing with underground installations, it's important to understand the different types of conduits and their suitability for such environments. Rigid metal conduit, RMC, offers excellent physical protection and is suitable for direct burial. Intermediate metal conduit, or IMC, provides a lighter weight alternative to RMC while still offering good protection. PVC conduit is a non-metallic option that is resistant to corrosion and suitable for direct burial when properly installed. LFMC, on the other hand, is primarily designed for flexibility and is typically used in shorter runs where bends or movement are required. When using LFMC underground, it's crucial to protect it from physical damage and moisture. Enclosing it in a rigid conduit or concrete encasement can provide the necessary protection. Proper sealing at all entry and exit points is also essential to prevent water from entering the conduit. Several factors should be considered during the installation. Firstly, the depth of burial must comply with local codes and the National Electrical Code. This ensures that the conduit is protected from damage caused by digging or other activities. Secondly, the type of soil and its potential for corrosion must be taken into account. If the soil is corrosive, additional measures may be needed to protect the conduit. Thirdly, proper grounding and bonding are essential to ensure electrical safety. This helps to prevent electrical shock and equipment damage. It's always recommended to consult with a qualified electrician or electrical inspector to ensure that the installation meets all applicable codes and standards. They can provide guidance on the best materials and methods for the specific application. They can also inspect the installation to ensure that it is safe and compliant. Furthermore, always follow the manufacturer's instructions for all electrical components. This includes conduits, fittings, and connectors. The instructions provide important information on proper installation and use. Ignoring the manufacturer's instructions can lead to unsafe conditions and equipment failure. Remember, electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others. If you are not comfortable working with electricity, it's best to hire a qualified electrician to do the job. In addition to the physical protection and moisture resistance, another critical aspect of underground electrical installations is proper grounding and bonding. Grounding provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock. Bonding connects all metallic parts of the electrical system together, ensuring that they are at the same electrical potential. This minimizes the risk of electrical shock if someone comes into contact with two different metallic parts. The National Electrical Code provides detailed requirements for grounding and bonding in Article 250. It specifies the types of grounding electrodes that are permitted, the size of the grounding conductors, and the methods for bonding different parts of the electrical system. Common grounding electrodes include ground rods, ground plates, and metal underground water pipes. The size of the grounding conductor depends on the size of the service entrance conductors. Bonding can be achieved by using bonding jumpers to connect metallic conduits, enclosures, and equipment. It's important to ensure that all connections are tight and corrosion resistant. Another important consideration for underground electrical installations is the potential for voltage drop. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or not operate at all. The National Electrical Code provides guidelines for minimizing voltage drop in Section 210.19 Informational Note 4 and Section 215.2 Informational Note 2. These guidelines recommend limiting the voltage drop to no more than 3% for branch circuits and 5% for feeders. Voltage drop can be reduced by using larger conductors, shortening the length of the circuit, or increasing the voltage. In some cases, it may be necessary to install a separate transformer to provide the correct voltage to the equipment. When designing an underground electrical installation, it's important to consider all of these factors to ensure that it is safe, reliable, and compliant with all applicable codes and standards. Consulting with a qualified electrician or electrical engineer is highly recommended to ensure that the installation is properly designed and installed. Furthermore, the selection of appropriate wiring methods and materials plays a crucial role in the longevity and safety of underground electrical installations. Apart from rigid metal conduit, intermediate metal conduit, and PVC conduit, other options exist depending on the specific application and environmental conditions. For instance, direct burial rated cables are designed for underground installations without requiring additional conduit protection. These cables feature a robust outer jacket that resists moisture, abrasion, and chemical exposure. However, local codes and regulations may impose restrictions on the use of direct burial cables in certain areas. Another factor to consider is the potential for ground movement or settling, which can exert stress on underground conduits and cables. Flexible conduits, such as liquid-tight flexible metal conduit or liquid-tight flexible non-metallic conduit, can accommodate some degree of movement without compromising the integrity of the electrical system. However, it's crucial to ensure that these flexible conduits are properly supported and protected from physical damage. Moreover, the choice of fittings and connectors is equally important for ensuring a reliable and watertight connection. Use only fittings that are specifically designed for the type of conduit being used and ensure that they are properly installed and tightened. When using PVC conduit, use PVC cement to glue the fittings together, creating a watertight seal. For metal conduits, use threaded fittings or compression fittings to ensure a secure connection. In addition to the technical aspects of underground electrical installations, it's also important to consider the environmental impact. Electrical equipment can generate heat, which can affect the surrounding soil and vegetation. It's important to choose equipment that is energy efficient and generates minimal heat. Also, take steps to minimize the disturbance to the soil and vegetation during the installation process. This can include using trenchless installation methods such as boring or tunneling to avoid digging up large areas of ground. It's also important to properly dispose of any waste materials generated during the installation process, such as scrap wire, conduit, and packaging materials. Recycle these materials whenever possible to reduce the amount of waste that ends up in landfills. By taking these environmental considerations into account, you can minimize the impact of underground electrical installations in the environment. Moreover, it is crucial to conduct thorough inspections and maintenance on underground electrical systems to ensure their continued safe and reliable operation. Regular inspections can help identify potential problems before they escalate into major issues. Look for signs of damage, such as cracks, corrosion, or water intrusion. Also, check for loose connections and damaged wiring. Maintenance tasks can include tightening connections, replacing damaged components, and applying protective coatings to prevent corrosion. It's also important to keep the area around the underground electrical system clear of vegetation and debris. This can help prevent damage to the system and ensure that it is easily accessible for inspections and maintenance. Keep detailed records of all inspections and maintenance activities. This information can be helpful for tracking the performance of the system and identifying any recurring problems. By implementing a comprehensive inspection and maintenance program, you can extend the lifespan of the underground electrical system and ensure that it continues to operate safely and reliably. Furthermore, staying informed about the latest advancements in electrical technology and best practices is essential for ensuring the safety and efficiency of underground electrical installations. The electrical industry is constantly evolving, with new products, techniques, and regulations being introduced on a regular basis. Staying up to date on these developments can help you make informed decisions about the design, installation, and maintenance of underground electrical systems. Attend industry conferences, workshops, and training sessions to learn about the latest advancements in electrical technology. Read industry publications, such as trade magazines and technical journals, to stay informed about new products and techniques. Follow industry experts and organizations on social media to get the latest news and updates. By staying informed about the latest advancements in electrical technology and best practices, you can ensure that your underground electrical installations are safe, efficient, and compliant with all applicable codes and standards. The importance of adhering to local codes and regulations cannot be overstated. Local jurisdictions often have specific requirements that go beyond the National Electrical Code, reflecting unique environmental conditions, construction practices, or community needs. These local codes may address issues such as burial depth, conduit types, grounding requirements, or inspection procedures. It is crucial to consult with the local building department or electrical inspector to determine the specific requirements for your project. Failure to comply with local codes can result in costly delays, fines, or even legal action. Moreover, compliance with local codes ensures that the electrical installation is safe and reliable for the community. In addition to the National Electrical Code and local codes, there may be other industry standards or guidelines that are relevant to underground electrical installations. These standards may be developed by organizations such as the Institute of Electrical and Electronics Engineers, or i.e., the National Fire Protection Association, or NFPA, or the American National Standards Institute, or ANSI. These standards can provide valuable guidance on issues such as grounding, bonding, surge protection, and equipment selection. It is important to be aware of these standards and to follow them whenever possible. Compliance with industry standards can enhance the safety, reliability, and performance of underground electrical installations. The documentation of underground electrical installations is essential for future maintenance, repairs, and upgrades. Accurate and detailed documentation can save time and money by providing valuable information about the location, type, and configuration of underground electrical components. Documentation should include a site plan showing the location of all underground conduits, cables, and equipment. The site plan should be to scale and should be referenced to permanent landmarks or property lines. Documentation should also include detailed drawings of the electrical system showing the size and type of conductors, the location of splices and terminations, and the grounding and bonding connections. In addition, documentation should include a bill of materials, listing all of the components used in the installation along with their manufacturer and model number. All documentation should be stored in a safe and accessible location and should be updated whenever changes are made to the electrical system. By maintaining accurate and detailed documentation, you can ensure that future work on the underground electrical system can be performed safely and efficiently. A comprehensive understanding of soil conditions is critical for the proper design and installation of underground electrical systems. Soil properties such as resistivity, thermal conductivity, and chemical composition can significantly impact the performance and longevity of underground electrical components. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity can increase the risk of corrosion of underground metal conduits and cables. Soil thermal conductivity is a measure of how well the soil conducts heat. Low soil thermal conductivity can cause underground cables to overheat, reducing their ampacity and lifespan. Soil chemical composition can also affect the corrosion of underground metal components. Soils with high levels of chlorides, sulfates, or other corrosive chemicals can accelerate the corrosion process. A geotechnical investigation should be conducted to determine the soil properties at the site of the underground electrical installation. The results of the geotechnical investigation should be used to select appropriate materials and installation methods. For example, if the soil resistivity is low, corrosion-resistant materials such as PVC conduit or coated metal conduit should be used. If the soil thermal conductivity is low, the cables should be deaerated to account for the reduced heat dissipation. And if the soil chemical composition is corrosive, the metal components should be protected with a suitable coating or wrapping. Taking soil conditions into account during the design and installation process can help ensure the long-term reliability and performance of underground electrical systems. The selection of appropriate backfill materials is crucial for providing adequate support and protection for underground electrical conduits and cables. Backfill materials should be non-corrosive, well-draining, and free of sharp objects that could damage the conduits or cables. Common backfill materials include sand, gravel, and crushed stone. The particle size of the backfill material should be selected to provide adequate compaction and support. The backfill material should be compacted in layers to prevent settling and to ensure that the conduits and cables are properly supported. The backfill material should also be sloped away from the conduits and cables to promote drainage. The use of improper backfill materials can lead to damage to the conduits and cables, resulting in costly repairs and downtime. The prevention of water ingress into underground electrical conduits and enclosures is essential for maintaining the integrity and reliability of the electrical system. Water can cause corrosion of metal components, short circuits, and other electrical problems. There are several measures that can be taken to prevent water ingress into underground electrical systems. Firstly, use watertight conduits and enclosures. Secondly, seal all conduit joints and fittings with a suitable sealant. Thirdly, provide adequate drainage to prevent water from accumulating around the conduits and enclosures. Fourthly, install a sump pump in any underground vaults or manholes to remove any water that does accumulate. Fifthly, inspect the underground electrical system regularly for signs of water ingress and take corrective action as needed. By taking these precautions, you can minimize the risk of water damage to underground electrical systems and ensure their long-term reliability. The protection of underground electrical systems from physical damage is essential for preventing disruptions to electrical service and ensuring public safety. Physical damage can be caused by a variety of factors, including digging, construction activities, and vehicular traffic. There are several measures that can be taken to protect underground electrical systems from physical damage. Firstly, bury the conduits and cables at a sufficient depth to protect them from digging and construction activities. Secondly, mark the location of the underground electrical system with warning signs and markers. Thirdly, use reinforced concrete or other protective materials to encase the conduits and cables in areas where they are exposed to vehicular traffic or other potential hazards. Fourthly, coordinate with local utility companies and contractors to ensure that they are aware of the location of the underground electrical system before they begin any digging or construction activities. Fifthly, inspect the underground electrical system regularly for signs of damage and take corrective action as needed. By taking these precautions, you can minimize the risk of physical damage to underground electrical systems and ensure their continued reliable operation.